Instagram hosts over 50 billion photos. Users upload an average of 95 million photos and videos daily. That's 1.1 million every single second. The challenge? Delivering that content blazingly fast to a global audience. Here's what most engineers get wrong when designing a system at this scale. They underestimate the read volume. By the end of this video, you'll know exactly how to architect a social media platform that can handle billions of users and serve millions of requests per second. We'll see how this matters when we discuss scaling.
Before diving in, let's define the scope. Functionally, we need to support user registration and login, photo and video uploads, feed generation, following and follower relationships, and notifications. Non-functional requirements include high availability, low latency, and eventual consistency for most data. Clarifying questions we should ask the interviewer: do we need to support direct messaging? What about stories or reels? For this exercise, we'll focus on the core features, feed and media sharing. We'll prioritize low latency because users expect near-instant access to content. High availability is crucial because any downtime can significantly impact user engagement. Eventual consistency is acceptable for non-critical data like follower counts.
Let's crunch some numbers. Assume 500 million daily active users, DAU. Each user uploads 2 photos or videos per day, averaging 3 megabytes each. That's 500 million times 2 times 3 megabytes equals 3 terabytes of new storage daily. Over a year, that's over 1 petabyte of new storage. For QPS, if 10% of DAU refresh their feed every second, that's 500 million times 10% equals 50 million feed requests per second. That's a huge number. For bandwidth, serving 3 megabytes per feed refresh means 50 million times 3 megabytes equals 150 terabytes per second. This estimation tells us we need a robust and scalable infrastructure. Stop. Think about this. These numbers drive every design decision we make. Remember the 50 million QPS we just calculated? We'll see how caching helps us handle that load. With the foundation in place, let's tackle the high-level design. We'll separate read and write paths. For writes, clients upload media to a load balancer, which forwards requests to the API gateway. The API gateway authenticates the user and routes requests to the app servers. Media files are stored in object storage like AWS S3. For reads, clients request their feed via the API gateway, which first checks the cache. Cache hits return immediately. Cache misses query the read replicas. Finally, we have a message queue for asynchronous tasks like generating thumbnails and sending notifications. We'll use Kafka because its append-only log provides replayability, ensuring we don't lose events if a consumer fails. SQS was considered, but it lacks Kafka's strong ordering guarantees. Here's the twist. The API gateway also handles rate limiting to prevent abuse. We'll use the token bucket algorithm for this. The API endpoint for uploading media would be post/API/v1/media, with parameters like long URL, custom alias optional, and expiry optional, returning a short URL and creation stamp time. Now let's dive into the core logic, feed generation and the social graph. For the social graph, we'll use an adjacency list representation in a graph database like Neo4j. This allows us to efficiently query relationships between users. We chose Neo4j because it's optimized for graph traversals, making relationship queries faster. A relational database would require complex joins. For feed generation, we have 2 options, push and pull. With a push model, when a user posts, their followers' feeds are immediately updated. This is great for low latency, but struggles with large fanout. With a pull model, feeds are generated on demand when a user refreshes their feed. This is simpler to scale, but can increase latency. We'll use a hybrid approach. For users with a small number of followers, we'll push updates. For users with many followers, we'll use a pull model. This is where most people go wrong, failing to account for high fanout scenarios. The algorithm we use for ranking is time-based ranking, where newer posts are prioritized. Your interviewer will push back here. Wouldn't machine learning ranking be better? ML ranking adds complexity and requires significant training data. For initial design, time-based ranking is simple and effective. We can add ML later as an optimization. An experienced interviewer will probe, what happens when a user follows 10,000 other users? We'll need to implement fanout queues to handle the write load. If the fanout queues back up, we might need to shed load by dropping notifications for less important events. Next, let's design the data model. We'll use a relational database like Postgres for structured data and object storage like S3 for media files.
For the user table, we'll have fields like user ID, primary key, username, password hash, email, created at, and updated at. For the post table, we'll have post ID, primary key, user ID, foreign key, media URL, caption, created at, and updated at. We'll also add an index on user ID for efficient feed retrieval. Pause and think. What's missing from this schema? We also need an audit field, job ID, for long-running asynchronous tasks. We choose Postgres because it provides ACID properties, ensuring data consistency. MySQL was considered, but Postgres offers better support for complex queries and data types. We'll use UUIDs for user ID and post ID to ensure uniqueness across shards.
Now, let's scale the system. We'll use caching extensively to reduce latency. We'll use a CDN like Cloudflare to cache media files closer to users. For feed data, we'll use a distributed cache like Redis. For database scaling, we'll use sharding. We'll shard the user and post tables based on user ID. This distributes the load across multiple database servers. We'll also use read replicas to handle read traffic. Remember those 95 million photos and videos uploaded daily? To handle that volume, we need a robust CDN. We use a cache aside pattern with Redis. On a cache miss, we query the DB and backfill the cache. This keeps our P99 under 50 milliseconds for read-heavy workloads. Your interviewer might ask, why not memcached? Redis offers richer data structures and persistence, which are beneficial for our use case. Specifically, we use Redis because it supports sorted sets, which are ideal for ranking feeds by time or score. Memcache only offers simple key value storage. We'll use consistent hashing for sharding to minimize data movement when adding or removing shards.
To ensure reliability, we'll implement fault tolerance at every layer. We'll use multiple load balancers to prevent a single point of failure. We'll replicate our databases and caches. We'll monitor all components using tools like Prometheus and Grafana, and we'll set up alerting to notify us of any issues. Rate limiting is crucial to prevent abuse. We'll use a token bucket algorithm to limit the number of requests per user. If a server fails, the load balancer will automatically redirect traffic to healthy servers. We can also implement circuit breakers to prevent cascading failures. This is like having a safety net at every level. We'll use a rules engine to filter out inappropriate content, ensuring a safe user experience. In summary, we designed a scalable and reliable social media platform. We separated read and write paths, used caching and sharding for performance, and implemented fault tolerance for reliability. The biggest bottleneck? Managing the social graph at scale. Next steps? We could explore machine learning for feed ranking and content recommendations. Remember, every design involves trade-offs. We gained scalability, but sacrificed some consistency. We also need a rules engine to filter out inappropriate content.
Join our community of engineers mastering software engineering, algorithms, and technical skills. Subscribe to stay connected and never miss a tutorial.